Hello, and thank you for joining me on this journey. Tonight, we will slowly drift into a future where the stars no longer light the night sky. The end of star formation, a time when the universe begins its transition into the vast, silent expanse of cosmic darkness. Imagine the soft, quiet ebb of energy as the final stars burn out, their light flickering for the last time. The once bright, radiant constellations that have guided humanity for eons will fade into shadow, leaving only the cold remnants of once glorious suns. Let your mind wander, exploring what this universe without light would feel like, as the stars, our ancient companions, slowly vanish into the deep void. If you enjoy these relaxing moments, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. In the vast expanse of the universe, the birth of a star is a quiet symphony of forces. It begins with a whisper, a faint stir of gas and dust scattered across the emptiness. These particles, woven together from ancient stardust, drift in delicate suspension, suspended in the deep, cold void of space. Here, within these dark clouds of molecular gas, the seeds of stars lie dormant, awaiting the spark that will ignite them. As the gas particles begin to clump together under their own gravity, the darkness thickens and pressure builds. Slowly, the cloud collapses inward, the force of gravity compressing the gas until it begins to heat up. The temperatures rise, and a quiet tension fills the space as the delicate balance between gravity and pressure holds the cloud together. For millions of years, the gas churns and compresses, and the first flickers of light begin to appear, hidden deep within the heart of the collapsing nebula. It is here, in the quiet depths, that a new star begins to stir, marking the beginning of a new chapter in the universe's endless cycle of creation. Gravity begins its slow, patient work. Over millions of years, it gathers the gas and dust into ever tighter clumps, each one more concentrated than the last. This is no random gathering. It is the invisible hand of the universe, coaxing the materials to come together. Slowly, like a dream taking shape, a dense core begins to form. The temperature rises as pressure builds within, and the gas, mostly hydrogen, becomes compressed, hot enough to begin the first stirrings of nuclear fusion. The collapse of gas under gravity is a delicate balance. For the process to continue, the heat generated from fusion must push outward, counteracting the relentless pull of gravity. This fine equilibrium defines the life of the star. As the core reaches a critical point, the fusion reactions explode into life, producing light and heat. The star has been born. Above the core, the gas surrounding the newborn star begins to shine, a brilliant glow, marking the birth of a celestial titan. These first stars, massive and radiant, are the building blocks of galaxies, scattering their light across the universe and becoming the beacons around which entire solar systems will form. Yet, their birth is not a singular moment. Rather, it is the continuation of an ancient cycle that has unfolded across the cosmos for billions of years. Each star, a fresh iteration of a cosmic process that has, for all its violence, birthed the very elements that make up the galaxies, the planets, and even life itself. But this process is not endless. The materials required to create stars, gas, and dust are not infinite. As the universe ages, stellar nurseries, regions of cold, dense gas where stars are born, become fewer and farther between. Over time, the cosmos will begin to run out of the ingredients necessary for new stars to take shape. The gas clouds that once filled the galaxies will gradually dissipate, leaving behind only the faintest traces of their former abundance. As the rate of star formation slows, it marks the beginning of an inevitable shift, a transition from a universe of vibrant, shining stars to one in which the birth of new stars becomes increasingly rare. The light that has so long illuminated the night sky will begin to fade, like the last embers of a fire that has consumed its fuel. In these stellar nurseries, where once gas and dust collapsed to form stars, the air will grow still. The brilliance of new stars will grow dimmer and dimmer, until finally these nurseries will fall silent, emptied of the raw material they once held in abundance. And yet, even as this slow death of star formation begins, there is a deep beauty in the process itself. The birth of a star is not only a cosmic event, but a profound manifestation of the universe's continual transformation, a reminder that life, in all its forms, is always in a state of becoming. And so, the universe continues its slow, majestic dance, one of creation, destruction, and recreation. In the heart of every newborn star, there is a story unfolding, one that has been written across the eons. These stars, bright and brilliant, will carry their light into the future, even as the cosmic cycle begins to slow. As they burn and fade, they leave behind the building blocks of the next generation, ensuring that the light of the universe will, in some form, continue to shine. A star's life begins not as a singular moment, but as an ongoing saga that stretches across millions or even billions of years. From the first glimmer of fusion in the heart of a collapsing gas cloud to its final faded embers, the evolution of a star is a journey marked by constant change. In the beginning, a newly formed star is a furnace of intense heat and energy, its core igniting the fusion of hydrogen into helium. This nuclear reaction generates the outward pressure necessary to counterbalance the inward pull of gravity, allowing the star to maintain its shape. But the balance is fragile. As the star consumes its hydrogen fuel, the pressure from the fusion decreases and gravity begins to win. The core contracts and the outer layers expand, transforming the star into a red giant. During this phase, the star swells dramatically, often many times its original size, as it begins to burn heavier elements. This expansion signals a dramatic shift in the star's behavior. The core, now composed primarily of helium, becomes hot enough to begin fusing these heavier elements into carbon and oxygen. The outer layers, no longer held in check, stretch farther and farther into space. The light they emit becomes cooler, casting the star in a reddish hue. This red giant phase may last for millions of years, as the star exhausts its supply of helium and prepares for the next stage of its life. Once the helium is consumed, the star faces a pivotal choice. Smaller stars, those with less mass, enter a phase of decline marked by the shedding of their outer layers, leaving behind only the exposed core. This core, now a white dwarf, slowly cools over time, no longer capable of sustaining fusion reactions. White dwarfs are incredibly dense, their mass similar to that of the Sun, but compressed into a size similar to Earth. Over the course of billions of years, these remnants will gradually lose their heat, slowly fading into cold, dark objects. For stars of greater mass, the end of the line is far more dramatic. These stars, having burned through hydrogen and helium, begin fusing even heavier elements: carbon, oxygen, neon, and eventually iron. As iron accumulates in the core, it marks the point of no return. Iron fusion does not produce energy, and the core can no longer support itself. The outer layers collapse inward with unimaginable force, triggering a violent explosion, the supernova. A supernova is a cataclysmic event that briefly outshines an entire galaxy, releasing energy equivalent to that produced by the star over its entire lifetime. This explosion not only destroys the star, but scatters heavy elements like gold, iron, and uranium across the cosmos. These elements, once locked in the star's core, become the building blocks for future generations of stars, planets, and life itself. But the death of a massive star does not end with the supernova. The core that remains may collapse into a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. Alternatively, if the mass is sufficient, the collapse continues and the core becomes a black hole, an object with such immense gravity that not even light can escape. These stellar remnants continue to influence their surroundings, their gravitational pull bending space and time itself. From birth to death, a star's life is one of transformation and decay. The elements created during its life and death are the foundation of the universe's matter. The iron in your blood, the calcium in your bones, the gold in your jewelry, all were forged in the hearts of stars. These heavy elements, scattered throughout space by supernova explosions, eventually coalesce to form new stars, planets, and even life. And so, the cycle continues, each star's death making way for the next generation of cosmic creation. Yet, as the universe ages, the number of stars decreases. The rate of formation slows, and the stellar nurseries, once abundant, become empty. Fewer stars are born, and those that remain burn out. What remains are the remnants of stars, dark and silent, floating through the vastness of space. The light they once emitted may have faded, but their legacy continues in the very fabric of the universe. As one star burns out, another will begin its own journey, but with each passing generation, the universe grows older and darker. In the vast emptiness of space, a hidden process is unfolding. Amid the darkness, swirls of gas and dust, often invisible to the naked eye, drift through the cosmos, forming the very foundation from which stars are born. These cosmic clouds, composed primarily of hydrogen and helium, are the building blocks of the universe. But they are not static. Their existence is the result of the delicate interplay of forces that shape the birth of stars, galaxies, and entire systems. At first glance, these clouds may appear to be featureless, cold, and diffuse. However, within them lies the potential for creation on a grand scale. Gravity is the unseen architect at work, pulling the scattered particles together, slowly compressing the gas and dust into denser clumps. Over millions of years, the collapsing cloud will shrink under its own weight, causing the particles within to collide and heat up. As the cloud contracts, the temperature rises. Eventually, the pressure becomes so great that nuclear fusion begins, igniting the birth of a new star. But not all regions within these clouds evolve in the same way. Some areas are colder, denser, and more isolated, while others are warmer and more diffuse. The cooling of gas plays a crucial role in this process. As gas cools, it becomes more susceptible to the force of gravity, allowing for a more rapid collapse. In the denser regions, gas particles begin to collide more frequently, their motions becoming more chaotic as they lose energy. The cooling helps the cloud contract even further, facilitating the birth of stars. Yet the collapse of gas and dust is not a straightforward event. There are forces at play that both hinder and help this process. On one hand, there are cosmic winds, streams of particles propelled by the radiation from nearby stars that blow through the gas clouds. These winds can disperse the gas, preventing the collapse from proceeding smoothly. Stellar winds, in particular, can blow away the lighter elements, leaving only the denser remnants behind. On the other hand, the radiation from these stars can also provide the energy needed to trigger the collapse of nearby gas clouds. In some cases, the shock waves from nearby supernova can compress gas clouds, sparking the birth of new stars. Forces like these, along with the inherent cooling and gravitational collapse, shape the conditions necessary for stars to form. The process is a slow one, on the scale of millions of years, yet it is also incredibly efficient. The clouds of gas and dust in stellar nurseries are dense enough to produce stars in large numbers. These regions of active star formation are known as nebulae, vast and vibrant structures teeming with the energy of creation. One of the most famous examples of a stellar nursery is the Orion Nebula, a region where gas and dust swirl in spectacular clouds, giving birth to hundreds of young stars. In this region, the pressure from the forming stars is so great that the surrounding gas is illuminated in shades of pink and blue, casting an ethereal glow across the dark expanse of space. These stellar nurseries, scattered throughout galaxies, are the heart of star formation, the cradles where the next generation of stars is born. Yet, as the universe ages, the clouds of gas and dust that fuel star formation are slowly being depleted. Over billions of years, the raw materials necessary to create new stars will begin to thin out. The hydrogen gas that makes up most of these clouds will be consumed by ongoing star formation, and the remnants of old stars will gradually disperse. As these materials fade, the rate of new star formation will slow. The nebulae will grow darker, quieter, and emptier. In the far future, the cosmic nurseries will be nearly extinct, and the birth of new stars will become a rare event. The galaxies will be left with only the stars that have already formed, many of them long past their prime, burning their last fuel in a dying glow. The silence that follows the death of star formation will be a reflection of the universe's fading vitality, a universe where the forces of creation are no longer at work, and the lights of new stars will no longer shine across the heavens. Still, the remnants of star formation, gas, dust, and the remnants of dead stars will persist, scattered across the darkened universe. These remnants may no longer give birth to new stars, but they will continue to shape the cosmos, their traces echoing through the void long after the last stars have burned out. In the grand theatre of the universe, there is no event more dramatic than the death of a massive star. These stellar giants, having lived their lives in a constant battle between gravity and nuclear fusion, reach a cataclysmic end. When a star exhausts its nuclear fuel, its core collapses in on itself, triggering a violent explosion, a supernova. This event is one of the most powerful in the cosmos, releasing more energy in a single moment than our sun will produce in its entire lifetime. A supernova is not just a spectacular flash of light and energy. It is the birthplace of many of the universe's heaviest elements. The tremendous heat and pressure generated in the explosion allow for nucleosynthesis, the fusion of lighter elements into heavier ones. During the star's life, Elements like hydrogen and helium were fused into carbon and oxygen. However, in the intense conditions of a supernova, the fusion continues, creating elements as heavy as gold, iron, and uranium. These newly created elements are scattered across space, carried away by shockwaves that travel outward from the star's core. The shockwave acts as a cosmic seed sower, distributing the essential building blocks for the formation of new stars, planets, and even life. Without these elements, the universe would remain barren, composed solely of hydrogen and helium. It is through these explosions that the complex, diverse chemistry required for life as we know it comes into existence. The creation of elements during a supernova is not confined to just one star. Every supernova enriches the surrounding space with heavier materials, adding layers of complexity to the galactic medium. Over time, these elements mix with the gas and dust in nebulae, where they become the raw materials for the formation of new stars. As a result, each generation of stars is built upon the ashes of the previous generation, contributing to the ongoing evolution of the universe. However, these magnificent explosions are not infinite. As the universe grows older, fewer stars are formed, and those that do form burn their fuel at an ever-decreasing rate. The frequency of supernova will diminish as the stellar nurseries, the regions where stars are born, grow emptier. Eventually, the stars capable of creating supernova will fade, and with them, the creation of new elements will slow. Without the explosive power of these dying stars, the universe will lose a critical source of material for the formation of planets, metals, and other complex substances. In a universe without stars, the remnants of supernova, the heavy elements scattered by the explosions, will remain, but they will no longer give birth to new stars. The building blocks of life, scattered across vast stretches of space, will become increasingly isolated, leaving a universe that is cold, dark, and devoid of new creation. Without the energetic forces of stellar death, the universe will fall into a state where the raw ingredients for future generations of stars will have been exhausted. Yet, for now, the supernovae continue, burning brightly against the dark backdrop of space. Each explosion serves as a reminder of the dynamic, cyclical nature of the cosmos. These events provide not only the raw materials for new stars and planets, but also the heavy elements that make up everything we know: our bodies, our Earth, and the very fabric of the universe itself. The universe, once a bustling cradle of star formation, is now entering an era of gradual decline. The stars that once dotted the cosmos in vibrant constellations are no longer being replaced in equal measure. Over billions of years, the raw materials for star creation, the gas and dust scattered across galaxies, have slowly diminished. This steady depletion is setting the stage for the end of an era, the death of star formation. At the heart of this decline is the gradual exhaustion of hydrogen, the most abundant element in the universe and the fuel that powers stars. As new stars form, they consume vast quantities of hydrogen gas, leaving behind a quieter, emptier space. Over time, the cosmic gas clouds, once dense and full of potential, are slowly emptied. With each generation of stars born, the supply of gas is diminished, unable to replenish itself as rapidly as before. This marks the beginning of a slow and inevitable decline in star formation. In addition to the depletion of hydrogen, another factor contributing to this cosmic slowdown is the increasingly rarefied nature of the stellar nurseries, the cold, dense regions where stars are born. As the universe expands, the gas and dust in these regions become more spread out, and the conditions necessary for the gravitational collapse required to form stars become less likely. Once, gas clouds were densely packed, able to collapse under their own weight, leading to the formation of stars. But as these clouds become thinner and colder, the very process of collapse becomes harder and harder to initiate. The absence of fresh star formation has far-reaching consequences. The stellar nurseries, once teeming with the birth of new stars, are gradually fading. Regions of the universe that were once vibrant with creation are now becoming ghostly, devoid of the energy and light that once defined them. The birth of new stars, once a regular and abundant event, will grow increasingly rare as the universe continues to age. The once luminous regions of galaxies will fall into darkness, leaving behind only the remnants of the stars that have long since passed their prime. In time, this decline will affect not just the local stellar populations, but the entire structure of the universe. As fewer stars are born, the remaining ones will age and burn out. With no new stars to take their place, the galaxies will slowly grow darker and emptier. The force of gravity, which once bound star systems together, will no longer have the same impact as stars begin to fade away. The universe will be left with only the remnants of what once was, a vast expanse of space filled with the silent traces of stars long gone. This gradual extinction of star formation is a natural outcome of the universe's evolving conditions. The cooling and spreading of gas clouds, the consumption of hydrogen, and the expansion of the universe itself all contribute to the cessation of new star births. As the cosmos moves into this new phase, the stars that remain will burn their fuel and fade into nothingness. The universe will grow darker, its once constant cycle of creation and destruction slowing to a near halt. The universe's slow shift from a place of continuous creation to one of stillness and quiet emptiness is inevitable. But within this cosmic decline, there is a sense of beauty, of cycles completed, of life and death on a cosmic scale. The stars, in their last flickers, will remind us of the forces that have shaped everything around us. And though their birthplaces are fading, the legacy of their light will live on in the remnants they leave behind, scattered across the cosmos. The twilight of a star's life is an event both beautiful and tragic, where the once blazing beacon of light begins its inevitable descent into darkness. As stars exhaust their nuclear fuel, the balance between gravity and radiation pressure begins to tip. With no energy from fusion to support them, they start to collapse under their own immense gravity, a slow but relentless decline. The brilliance they once radiated slowly fades, transforming these celestial giants into the faintest of embers. First sign of a star's nearing death is the expansion of its outer layers, swelling into a red giant, or, in the case of even more massive stars, a supergiant. At this stage, the star's core is no longer able to fuse lighter elements like hydrogen and helium. Instead, it turns to heavier elements, such as carbon and oxygen, creating a more complex and unstable nuclear environment. As the outer layers of the star stretch far out into space, they shed enormous amounts of mass. Winds of hot gas blow away the outer shell, leaving behind a hot, dense core. This remaining core may take one of several paths, depending on the mass of the original star. For smaller stars, those with a mass similar to the Sun, the core becomes a white dwarf. These remnants are incredibly dense, yet no longer capable of nuclear fusion. Over billions of years, the white dwarf will slowly cool, fading into an invisible, cold ball of matter. Even though it no longer shines brightly, its existence remains a testament to the long life of the star that once was. In this final stage, the star's influence on its surroundings is felt only in the subtle gravitational pull it exerts, a lingering presence that continues to drift through the cosmos. For more massive stars, however, the end is far more dramatic. Their cores collapse with greater intensity, triggering a catastrophic explosion, a supernova. The force of the explosion propels the star's outer layers into space, scattering heavy elements into the interstellar medium. What remains of the core becomes either a neutron star, or, if the star is massive enough, a black hole. A neutron star is an astonishingly dense object, made mostly of neutrons packed together so tightly that a single teaspoon of material would weigh billions of tons. These stars are often found spinning at incredible speeds, emitting pulses of radiation as they rotate. The most extreme of these remnants is the black hole, an object with gravity so strong that nothing, not even light, can escape its pull. The core of the star collapses into an infinitely small point known as a singularity, surrounded by the event horizon, beyond which no information can return. Although black holes are invisible to the naked eye, their presence is felt in the space around them, warping time and space itself. Their powerful gravitational forces pull in everything in their vicinity, bending light and distorting the fabric of the universe. Even though these remnants no longer shine with the same brilliance as they did in their earlier lives, they continue to affect their environments. The cooling white dwarf drifts alone in space, its light gone, but not its gravitational influence. Neutron stars send out regular pulses of radiation, detectable by astronomers on Earth, while black holes consume matter from their surroundings, quietly reshaping the very structure of space. These remnants, though silent and unseen, remain powerful actors in the universe, even as their stellar ancestors burn out and fade away. The last glimmer of starlight is a fading memory, a final spark in an increasingly darkened cosmos. As these dying stars collapse, explode, or cool, they mark the end of an era, a time when the universe was alive with the energy of creation. As their light flickers out, the universe will enter its final still phase. But the remnants of these stars will persist, forever drifting through the cosmic void. In the aftermath of a star's death, the remnants left behind are not merely empty husks. Instead, they become some of the most mysterious and fascinating objects in the universe. Among these, neutron stars and black holes stand out as the most extreme, their gravitational forces bending the very fabric of space and time. These dark titans rule over the remnants of stars, their power and influence reverberating across the cosmos long after the stars themselves have burned out. Neutron stars are born from the collapse of massive stars that have exhausted their nuclear fuel. When the core of a star collapses, its protons and electrons are crushed together, forming neutrons. The result is an object so dense that a single cubic centimeter of a neutron star weighs billions of tons. These remnants are incredibly small, typically only about 20 kilometers across, yet they contain more mass than the Sun. Their intense gravitational field distorts the space around them, and their rotation speeds are staggering. Some neutron stars spin several hundred times per second, creating a powerful magnetic field that accelerates particles to near the speed of light. These rapidly spinning neutron stars are often referred to as pulsars, as they emit beams of radiation in regular pulses. The radiation emitted by pulsars is a result of the star's magnetic field and rotation. As the neutron star spins, the magnetic poles sweep across the sky, sending out beams of radiation that can be detected from great distances. These pulses of light are not steady, but rather occur at precise intervals, giving pulsars their name. The speed and regularity of these pulses are so precise that pulsars have been used as cosmic clocks, helping scientists measure time and study the fabric of space. Despite their small size, neutron stars exert an immense influence on the surrounding space, with their gravity bending light and warping the path of nearby objects. While neutron stars are already astonishing in their density and power, the most extreme remnants of a star's death are black holes. These enigmatic objects are formed when the core of a massive star collapses to an infinitesimally small point, creating a singularity surrounded by an event horizon. The singularity is a point of infinite density, where the laws of physics, as we understand them, cease to apply. The event horizon marks the boundary beyond which nothing, not even light, can escape the black hole's immense gravitational pull. Black holes are invisible to the naked eye because they do not emit light or radiation that can be detected. However, their presence is known by the way they interact with nearby matter. When a black hole's gravity captures nearby gas, dust, or even stars, the material is pulled toward the event horizon, creating a bright accretion disk as the material heats up and spirals inward. This disk can become incredibly luminous, emitting radiation across the electromagnetic spectrum. Despite their lack of visibility, black holes leave an indelible mark on the universe, warping space and time around them and affecting the orbits of nearby stars and gas clouds. In the far future, as the number of stars dwindles and the universe grows darker, black holes may become the last remnants of a once vibrant cosmos. Their gravitational pull will continue to shape the universe long after the stars have burned out. As the universe ages, black holes will slowly consume everything in their path, including the remnants of dead stars. Some black holes may even merge, forming larger and more powerful objects. Yet, even as they grow in size and power, the true nature of black holes remains elusive. The singularity at their core remains one of the greatest mysteries in physics, a place where the laws of general relativity and quantum mechanics collide. As the universe continues to evolve, black holes may be the only objects left to explore, their mysteries growing deeper as time marches on. In a universe without stars, these dark titans will stand as the final witnesses to the cosmic drama, a universe that was once teeming with light and energy, now reduced to the remnants of its once vibrant stars. In the far reaches of time, the universe will enter its final phase. The vibrant stars that once fueled the cosmos will have burned out, leaving behind nothing but the cold, fading remnants of their existence. The once dynamic dance of galaxies and stars, propelled by the forces of gravity and energy, will slow to a halt. Over billions of years, as the universe expands and energy spreads out, it will eventually reach a state known as heat death. In this distant future, the universe will become a dark, cold, and lifeless expanse, its potential for new creation extinguished. At the heart of this inevitable fate lies the concept of entropy, the measure of disorder in a system. The second law of thermodynamics tells us that entropy will always increase in a closed system. Over time, energy will spread out and become increasingly difficult to harness. Stars, which once acted as the cosmic engines of the universe, will no longer shine. As they burn through their fuel and their remnants decay into white dwarfs, neutron stars, and black holes, the energy that powered the universe will gradually disperse. As the energy in the universe spreads out, it becomes less concentrated. The once hot and dense stars, galaxies, and nebulae will cool and thin out. Without the energy from new stars, the complex processes that sustain life and growth will cease. The galaxies, no longer bound together by the gravitational pull of stars, will drift apart. The once mighty clusters will lose their cohesion, and the stars within them will become isolated, wandering through the vastness of an ever-expanding universe. The gradual loss of energy will affect even the most extreme objects in the universe. Black holes, the densest and most powerful remnants of dead stars, will not remain indefinitely. Though they are often thought of as eternal, even black holes will eventually evaporate. This phenomenon, known as Hawking radiation, occurs when quantum effects near a black hole's event horizon cause it to lose mass over time. As they radiate away energy, black holes will shrink and, over the course of trillions of years, vanish completely. The last black holes will slowly fade, leaving behind no trace of the immense gravitational forces they once exerted. The final stages of the universe's evolution will be marked by an absence of active processes. With no stars to fuel energy cycles, no galaxies to churn through the cosmos, and no black holes to distort space-time, the universe will enter a state of stasis. The only remaining remnants will be the cooling cores of white dwarfs and the slowly dissipating traces of energy left in the wake of the universe's past activity. These remnants, though still present, will no longer be capable of sustaining any meaningful interactions. In this dead universe, even the faintest traces of energy will be too sparse to form new structures or spark new life. The concept of heat death implies a final, irreversible dispersal of energy. With all the energy spread thin across the vastness of space, there will be no more opportunities for new stars to form, no fuel for the light of creation to ignite. The universe will have entered a state where everything is uniformly cold and dark, its past brilliance lost to time. It will be a place where the thermodynamic clock has run out, leaving behind only a sterile void, devoid of life, motion, and change. In this cold, dark expanse, there will be no sounds, no light, no energy to propel the cosmic story forward. The universe will continue to expand, but it will be an expansion into emptiness, a universe where the cycle of birth, life, and death has ceased. The final remnants of a once thriving cosmos will drift in isolation. The energy they once held, now scattered so thinly across space that it will be impossible to reassemble. The heat death of the universe represents the end of time itself, a future where the cosmos has become a frozen, lifeless place. As the stars that once illuminated the universe flicker out, the cosmos will be left with its final survivors, objects that carry within them the echoes of a time long past. These remnants of dead stars, white dwarfs, neutron stars, and black holes, will continue to exist long after the last star has burned out. while the universe as a whole will grow darker and colder. These objects will persist, each with its own slow fate, in a universe that has largely lost the energy that once defined it. White dwarfs, the remnants of medium-sized stars, will continue to drift through the cosmos in the absence of new stars. These dense, faint objects were once the hot cores of stars that exhausted their nuclear fuel. Without the energy of fusion to sustain them, white dwarfs slowly radiate away their remaining heat. Over billions of years, they will cool, growing dimmer and colder as they lose energy to the surrounding space. The once brilliant stars that gave rise to these objects will be nothing more than a memory, their light reduced to the faintest glimmer of what they once were. The cooling of white dwarfs will take place on a timescale that is almost beyond comprehension. Over trillions of years, these remnants will become cold and dark, their surfaces so cool that they will no longer emit detectable radiation. Eventually, they will fade completely into the void, leaving behind no trace of the stellar objects they once were. In a starless universe, these remnants will stand as the only physical markers of a time when stars still burned brightly, but they will be distant and isolated, unable to spark new activity or bring about any new creation. Neutron stars, formed from the collapse of more massive stars, are some of the densest objects in the universe. These compact remnants, often just 20 kilometers across, contain as much mass as several suns compressed into a sphere the size of a city. Despite their incredible density and intense gravitational pull, neutron stars are not immune to the passage of time. Slowly, over billions of years, neutron stars will lose their energy, with the pulsations that mark their rapid rotations growing weaker and less frequent. Some neutron stars will continue to emit faint radiation as they spin, their magnetic fields sweeping across the universe in regular pulses. But as time wears on, these pulsars will fade, leaving behind only their gravitational influence on the surrounding space. The most enigmatic of all the remnants are black holes. These objects, born from the collapse of the most massive stars, are capable of warping space and time itself. A black hole's gravity is so intense that it traps everything within its event horizon, including light. Black holes will continue to exist long after stars have vanished. However, even they are not eternal. Through a process known as Hawking radiation, black holes lose mass over time as they emit subatomic particles. This radiation causes them to gradually shrink, until eventually they disappear entirely. The process is incredibly slow, with the largest black holes taking trillions of years to evaporate completely. As black holes slowly lose mass, their role in the universe will gradually shift. Once cosmic giants, pulling in gas, dust, and even stars, they will no longer have the same power as the universe grows darker and emptier. With fewer stars and galaxies, black holes will be left adrift in the cold, vast expanse of space, their influence diminishing as their surroundings become more isolated. No longer fed by the abundant material they once consumed, these objects will drift farther from one another, their once active gravitational pull growing weaker. In the distant future, the last remaining black holes will be the only survivors of a once vibrant cosmos, standing as solitary remnants of a universe that has lost all the light it once knew. These dark beacons will serve as faint, almost invisible reminders of a time when stars filled the skies. Though still immense, they will become detached, isolated, floating through the endless space, their once dominant role in shaping the universe fading into the distance. In addition to these compact remnants, the universe will also be left with scattered particles of cosmic dust. These tiny fragments, the building blocks of stars and planets, will remain, but they will be too diffuse and cold to form new stars. The material that once created vibrant, energy-rich systems will now drift through space, no longer capable of initiating the complex interactions that once gave rise to life and energy. As the universe continues to expand, all that will remain are these final remnants: the cooling white dwarfs, the fading neutron stars, the slowly evaporating black holes, and the scattered dust. A lone observer drifting through this cold and empty universe would see only the faintest traces of the past, distant, dim glows from dead stars, and the occasional flicker of a black hole devouring the last remnants of cosmic matter. The darkness will be overwhelming, the stillness almost oppressive, as the last vestiges of activity vanish into the void. Yet, in this final phase of the universe's existence, there is a strange beauty in the remnants that remain. These objects, though no longer capable of creating or sustaining life, continue to carry the legacy of their starry ancestors. They are the quiet witnesses to an era that has passed, the final reminders of a time when the universe was full of light, energy, and motion. Their persistence, though slow and imperceptible, will last for eons, until, in the end, even they will be gone. In their stillness, these remnants hold a certain kind of dignity. Each white dwarf, each black hole, each fragment of cosmic dust is a chapter in the story of the cosmos, a story that will never truly be erased, even as the universe empties of stars. The energy that once fueled the brilliance of galaxies has long since dissipated, yet the remnants remain, not as living forces, but as echoes of the past. It is in this quiet endurance that the beauty of the universe's journey is most evident. They are the final whispers of a time when creation was active, when the skies were filled with the light of countless stars. Though their radiance is no longer visible, their presence endures, a testament to all that came before. As the stars fade from the heavens and the last remnants of a once vibrant universe slip into the void, one lone observer drifts silently through the cosmos, witnessing the final moments of a starless world. This solitary figure, alone amidst the vastness of space, sees the universe in its final stages, the once glittering galaxies reduced to lifeless voids, the dying embers of distant stars flickering weakly before they vanish completely. Time, once measured by the pulse of new stars, now stretches out infinitely, each moment a reminder of the inevitable end that has already begun. The vast silence that surrounds this lone observer is a companion, a constant presence as the last traces of light and life slowly vanish. The journey of the lone observer is not just physical, but emotional. Each step through this darkened cosmos is an encounter with the passage of time itself. Where once there was a galaxy teeming with stars, planets, and possibility, there is now only emptiness. The observer moves through this empty universe, their path silent, their presence barely a whisper in the cosmic vastness. And yet, despite the overwhelming stillness, there is a certain serenity in their journey, a quiet contemplation of the long arc of existence, stretching from the birth of the first stars to the slow decay of the universe. In the distance, the last stars flicker. They are no longer the bright beacons of energy and creation that once defined the cosmos. These stars are old and dying, their light faint and tenuous. The observer watches as the star's light grows dimmer with each passing moment, until they vanish altogether, leaving behind only the faint traces of their former brilliance. Some stars will collapse into black holes, their final moments marked by the bending of light and the swallowing of everything within reach. Others will fade into white dwarfs, slowly cooling and losing their remaining heat over billions of years. But all will eventually be gone, leaving behind a universe emptied of the fiery brilliance that once filled the night sky. As the last stars burn out, the galaxies that once glowed with the light of billions of stars grow increasingly distant, their starlight fading into the expanding darkness. The observer, now truly alone, watches the last flicker of life in the universe slowly die away. The remnants of these galaxies are scattered, drifting farther apart as the universe continues to expand, the space between them growing ever larger. What was once a bustling, interconnected network of cosmic structures is now a solitary scattering of objects, each moving further and further away from the others, their gravitational bonds weakened by the slow, inexorable stretching of space. With no stars left to guide the observer's path, the darkness becomes absolute. The observer floats in a cold, empty universe, their journey now devoid of any reference points. The very fabric of space around them has been stretched so thin that there are no longer any places of refuge, no nearby stars or nebulae to offer a momentary distraction from the overwhelming solitude. Only the faintest whispers of cosmic radiation remain, a background hum from a time long past, barely detectable by the observer's senses. In this darkened cosmos, the observer finds themselves in a constant state of drifting, untethered to any source of energy or light. What remains in this starless universe is not the blazing brilliance of creation, but the slow fading of all that once was. The observer, though isolated in the vast emptiness, finds a sense of stillness that transcends the loss. There is beauty in the silence, a kind of quiet reverence for the passage of time and the transformation of the universe. Every inch of space is now a memory of what came before, a universe filled with life and motion, now reduced to a barren, empty shell. The observer reflects on the cycles of life and death that have played out across the cosmos. The birth of stars, the creation of planets, the flourishing of life on distant worlds. These events, once so vibrant and full of potential, have now all come to an end. The great forces that shape the universe, the nuclear reactions in the cores of stars, the gravitational pull that bound galaxies together, are no longer active. The universe has entered a phase of stillness, a time when the energy that once fueled the cosmos has dissipated, and only the faintest traces of that energy remain. In the distance, a black hole looms, its gravity pulling everything nearby into its grasp. The observer watches as it consumes the last remnants of matter in its path, its event horizon swallowing everything within reach. This black hole, though invisible, has become a symbol of the final phase of the universe's life, a stage where even the most massive objects are slowly consumed and lost to the endless void. The observer, though unable to escape this cold, dark fate, is aware that their journey will eventually end in a similar manner, an inevitable plunge into the void, where all that remains is silence. Yet, even in the face of such isolation and entropy, the observer finds a certain sense of wonder. Despite the overwhelming darkness, the universe continues to exist, albeit in a form that is almost unrecognizable. The faint remnants of stars, the distant gravitational pull of black holes, and the scattered cosmic dust all serve as markers of the past. A past when the universe was full of energy and light. The observer, though they are the last to witness these remnants, is connected to a far-reaching history stretching back to the very first moments of creation. As the observer continues their journey through the silent expanse, they are left with only one certainty. The universe, in all its majesty and complexity, has followed its course. And now, in its final days, it has transformed into something different, something still, vast and empty. But within this emptiness, there is still a quiet kind of beauty, a deep and profound understanding of the passage of time, and a recognition that even in the absence of stars, the journey itself remains significant. In this stillness, the observer finds a sense of peace. The weight of all that has come before, the birth of stars, the birth of life, the countless moments that once filled the universe with energy and light, lingers, soft and eternal. The observer drifts, not lost, but gently carried forward by the silent momentum of time. As they look out into the infinite expanse, they understand that the universe, in its quiet and final form, is not empty at all. It is full of meaning, full of memory, and in that realization, the journey continues, even if only in thought. The stars may be gone, but their light has left a mark that cannot fade, and the observer, in their solitude, carries that light with them into the forever of the cosmos. As our journey through this fading universe comes to a close, allow yourself to sink even deeper into relaxation. Picture the quiet, ethereal transition, the stars now a memory, their soft glow extinguished, leaving behind only the vast, silent stretch of dark space. Feel the calmness of this cosmic journey, the quiet beauty of a starless sky. As the observer in this distant future, let yourself rest in the peaceful silence, where time moves slowly and the vast expanse of the universe unfolds in eternal darkness. Feel your thoughts gently fading, your muscles softening, and your breath flowing naturally and effortlessly. Rest here, fully supported in this safe and serene space. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.